Food processing facilities operate under standard macroscopic controls. Airflow is filtered, doors are sealed, and waste is systematically removed to maintain environmental stability. These defenses are routinely bypassed by rapid kinetic events, like an insect striking an electronic pest trap. Upon impact, the biological mass instantly shatters. The organism fractures into thousands of microscopic droplets, projecting them outward in a high-velocity burst. These invisible bioaerosols can distribute pathogens across a 6-foot radius in less than a second. Gravity pulls this suspended biological matter downward to settle directly onto stainless steel food preparation surfaces. The droplet's physical mass acts as a structural shield, protecting the internal pathogens and redefining the hygiene challenge as a complex problem of particle physics. One of the most concerning pathogens found in these droplets is the Hepatitis A virus. This specific virus exhibits extreme environmental resilience. It remains infectious even after exposure to intense heat and highly acidic environments. When aerosolized droplets settle undetected on work surfaces, the virus transfers into the food supply chain. To neutralize surface pathogens, safety engineers typically deploy ultraviolet C LED irradiation. A critical flaw stags the calibration of these systems. Engineers rely on linear log reduction mathematics, specifically the D10 value, to calculate the required UVC dose. Neutralizing aerosolized hepatitis A requires a departure from linear calculations toward nonlinear Weibull modeling, paired with precise 279 nanometer UVC technology. To understand calibration failure, examine viral architecture. Left is an enveloped virus, like SARS-CoV-2. Right is hepatitis A. Enveloped viruses are bound by a fragile lipid layer. UVC photons easily penetrate and denature this membrane, causing rapid structural failure. Hepatitis A is a non-enveloped virus. Its genetic material is encased inside a highly rigid icosahedral protein capsid. Within this capsid, specific structural proteins, known as VP4, bind the particle together, providing intense resistance to neutralization. Because of this structural density, the virus demands drastically higher inputs of UVC energy to achieve total RNA destruction. Biological armor dictates the minimum engineering baseline. Treating a resilient capsid like a standard respiratory virus leads directly to disinfection failure. This chart compares the energy needed for a 1 log reduction of aerosolized hepatitis A using 2 UVC wavelengths. The 255 nanometer system requires a massive surface dose of 76.5 millijoules. In contrast, the 279 nanometer system achieves similar reductions using only 8.1 millijoules. Wavelength depth does not correlate linearly with efficacy. The 279 nanometer system is vastly more efficient at penetrating this non-enveloped viral structure. Researchers also examined the substrate surface, comparing porous stainless steel against smooth glass. Despite differences in surface porosity, the inactivation rates on glass and stainless steel were statistically identical. Analytical. Since the surface material does not alter the survival rate, the liquid matrix of the bioaerosol itself serves as the primary physical barrier. This matrix obstruction creates a measurable anomaly known as the tailing effect. Aerosolized microscopic droplets do not land uniformly. They overlap and stack, creating distinct top and bottom layers of organic matter. Vertical UVC photons easily penetrate the top tier, but the surrounding liquid scatters and absorbs the light before reaching the bottom. This exposed top layer of viruses is neutralized quickly, registering as a steep initial drop in the viral load. The underlying hepatitis A viruses survive much longer because they are shielded by the neutralized biomatter resting above them. This dynamic creates a non-constant rate of inactivation. The longer the light stays on, the less efficient it becomes at penetrating the lower depths. The physical obstruction of overlapping droplets makes a constant linear kill rate mathematically impossible in a real-world environment. This chart plots experimental hepatitis A inactivation data over time. Standard D10 values attempt to draw a perfectly straight line through the data. However, as the tailing effect occurs, the real-world data points curve sharply away, yielding a low statistical fit. Relying on this linear model in industrial settings leads to severe underdosing, as the system shuts off while active hepatitis A remains on the surface. To correct this, engineers must apply the nonlinear Weibull distribution model. The Weibull equation introduces a critical shape parameter known as P. This parameter specifically accounts for the decreasing rate of viral inactivation caused by droplet shielding. Bioaerosol shielding creates a convex curve where P is less than 1. Factor this in, and the Weibull model perfectly intersects the tailing data points with near-perfect accuracy. With the accurate curve established, the D10 value is discarded and replaced by the delta value. The delta value represents the true dose needed for a 1 log reduction under the Weibull curve. For aerosolized hepatitis A, the required 279 nanometer delta sits between 5.21 and 6.67 millijoules per square centimeter. The Weibull model captures the biological reality that the linear D10 model ignores. Industry-standard D10 values fail to account for the physics of wet, aerosolized viral deposits on industrial surfaces. For non-enveloped viruses, 279 nanometer UVC LEDs provide the targeted optimum wavelength, superseding legacy 255 nanometer assumptions. Engineers must set baseline expectations for much higher dose thresholds, targeting a delta of 6.67 millijoules when dealing with resilient capsids. Automated safety systems must utilize Weibull shape parameters to accurately predict true inactivation times. There is a final layer of real-world complexity. While laboratory data relies on saline matrices, actual outbreaks involve aerosolized vomitus or fecal matter. Heavy organic loads in these biological matrices will exponentially exacerbate the tailing effect, requiring even more aggressive adjustments to the Weibull curve. True industrial scalability relies on the precise, nonlinear mathematical modeling of light attenuation to account for the physical obstructions of the production environment.